really like a build up to next week when we do our games. Okay, on Monday you're gonna start making your game, and we are going to play each other's games on Thursday. Okay, uh, we're going to talk about mathematical expectation. I sometimes will interchange that with expected value. Means the same thing. But essentially, what we are finding is how much either a player is expected to win or lose each time they play a game, or on the flip side, how much is the dealer or the house expected to win or lose each time their game is played. Okay? So we're really thinking of like a carnival or a casino type setting. Okay? Now, if we're going to a carnival or when you are 21, if you choose to go to a casino, those games are set up for who to make money? The house, not you. Okay? But we're still drawn to them in some way. Some of us. Because there's always a chance of winning. But let's talk about the math behind how they're set up to make money. Okay? So what we're going to do to calculate mathematical expectation is we're going to make this little table. So we're going to talk about all of the probabilities of winning, losing, breaking even, potentially. We're going to calculate all those probabilities, and then we're going to assign a value to them. Okay? If you lose $1, you would assign a -1 value. If you break even, you could assign a 0. Okay, if you win $10, you can assign a +10 to that. Okay, whatever you're coming out ahead or behind, you would assign that value to that probability. And then what we're going to do is we're going to take the probability times the value, probability times the value, probability times the value, and when those get added together, we have a mathematical expectation. What is expected to happen each time the game is played? Okay. Now, if we are talking about all the possibilities, what should be true about these probabilities? If I have every single scenario calculated out, then our probabilities should add up to 1. And I will look for that. Okay? So go ahead and read through example 1 for me, please. Okay, now if we were to talk about the mathematical expectation of roulette in general, it would get very, very complicated because there's also choice in the matter. They're choosing what to bet on, and then they're they're spinning the wheel. Okay, we're just going to consider a person coming up to the roulette table and betting red. Okay, that's the only thing that we're going to consider. And if that was the only part of the game, what would the mathematical expectation be? Does that make sense? Okay, it'd be too complicated to do the whole roulette in general. So first of all, let's talk about our sample space. What sort of slots do we have? What could our ball land in?
Red, black.
Okay, we have red, and how many of those are there? Okay, so I'm not going to write red 18 times, but I'm just going to make a note to myself that there's 18 of them. There's black, how many? And then there's green, right? And how many of those? Okay. So how many items are in our sample space? 38. Okay. So what's the probability of winning? We win if our ball lands in what color?
The color we pick.
Okay, so since we're picking red, how many reds are there? So the probability of winning is 18 out of 38. The probability of losing, what's the probability that it doesn't land in red? Okay, so now we're going to create our distribution. So we have value with probability. Okay, now I should say, in this example, it's very, I want to say black and white, but it's kind of black and red, right? It's either you win or you lose. And there's one way to win, and then any other possibility is a loss. Okay? There are games where there's more than one way to win, and there's different tiers of winning. Like maybe we could win $1 or $5 or $20, or we could break even, or we could lose, and losing's just losing. But in this chart, we only have two possibilities. That will rarely happen. Okay, but we're just going to start simple. So we have an 18 out of 38 chance of winning. Now, if we walk away from the table after we land on red, we would be up how much? $1. We would be up $1. So that's the value we're going to assign to it. The probability that we lose is 20 out of 38. And since the game costs $1, if we don't win anything, we are out $1. What? Okay. So our mathematical expectation, sometimes you'll hear me call it expected value. We are going to take value times probability plus value times probability. Okay, which just ends up being what? -2 over 38? Give that number to me in 4 decimal places. Two, what's the next one? 2.6? Yeah. Okay, we'll do that. Okay, so a couple things I want to point out. Come back to our chart. Notice how our probabilities add up to 1. And I didn't reduce our fractions just so I could make that point. Our probabilities add up to 1. Okay, we took probability times value to add them together to be this. Okay, did I make 2 decimal places? That's cool. Okay. Yes.
Do our values have to add up to 0?
No. Your values can be anything. Okay? If our value is negative, does that mean we are winning or losing? And how much are we losing? 5 cents. Every time we play the game, we can expect to lose 5 cents. That is what that means. Every time you play, you're expected to lose 5 cents. Now, is it practical that if I play one game, I can lose 5 cents? No. But if you play the game over and over and over and over and over, you're going to win some, you're going to lose some, but by the end of the day, you're going to lose 5 cents each time you play. Yes?
Does that change when we increase like value and stuff like that?
For this, if we would bet $2, then our values would be +2 and -2. So it wouldn't change the expected value.
So,
do you see what I'm saying?
well, so we're still expected to lose 5 cents.
Mm-hmm.
Okay. So if you bet $100, it's still.
Then your values would be +100 and -100. And when you multiply by the probabilities, you're still going to get this number. Okay? Now, what does this mean? If you played the game 100 times, how much money would you expect to lose?
5 times.
Okay, you're going to take 100 and multiply it by your expected value. Okay? You're going to lose $5.26 after you play 100 times. So however much cash you came into the casino with, you're losing with $5 less, is what that means. However, what does that mean for the house? They're making that. Okay, so as the dealer, I am making, so I would have a positive 0.0526 per game. So I would be making 5 cents per game from my client. Okay, I don't know what they call him, but whatever. And after 100 times, the dealer would make $5.26. After 200 times, the dealer would make $10.52. Okay. Questions about that? If the expected value is negative, you're losing money. If the expected value is positive, you're gaining money. Whatever it is for the house, it's going to be opposite for the player, because if the house is winning, the player is losing. Is that your question?
It was like the value thing if it just swaps.
Yep. Okay. So, if we think about the grand scheme of things, is this a game that the casino is going to put a lot of time and energy in? Like if it were just this, they're not making a whole lot of money off of that. Okay, but it could like be exciting to the players because like you're gonna win and you're gonna lose, but you're gonna win often enough to where you think you're making money.
But like the actual game, like there's like 30, you have to choose a number too, so like
Right.
they make like a
Yes,
lot.
the actual game is too complicated for us to do in this scenario.
Wait,
Okay.
oh,
Do they
so
make
you
more
only
money?
1 out of 38 chance of actually winning.
Basically.
Cool, because
Well, because you can either bet on a color or a number.
oh, really? Oh, but you
You
make
just win
more.
less if you bet on only a color.
Yes.
Okay.
Yes, like you win what you bet if it's just a color is what this is saying, but then there's different levels of, which is why like when we go to make our games next week, we're gonna have to be very careful with what our rules are because we don't want them to be too simple, but we don't want them to be too complicated. Okay, go ahead. This is pretty different from kind of the expected casino style of game. Go ahead and read through example 2. Okay, so what's our sample space? We have 6 $1 envelopes and 2 $5, 1 $10, and 1 $20. Okay, those are all of our possibilities. Okay, let's talk about the probability of winning. How many ways are there to win? There's a 1 out of 10 chance that you get the $10 bill. There's a 1 out of 10 chance that you get the $20 bill. So total, there's a 2 out of 10 chance of winning. Okay, so here's an example where we have different tiers of winning. Okay, so winning in general, we have 2 out of 10, but when we come down here to our distribution, we'll break it up into 1/10 and 1/10. Yes.
So evening out doesn't count as winning.
No, breaking even is not winning, and it's not losing either. So our probability of losing is not 8/10. What is it?
6.
It's 6/10. Okay? Because there's 6 ways to lose money. These two we're breaking even because we're paying $5 and getting $5. So when we set up our chart here, okay, we have a 1 out of 10 chance of getting that $20 bill, which means we would be up how much? We have a 1 out of 10 chance of getting the $10 bill. So we would be up $5. We have a 2 out of 10 chance of breaking even. I know that the value is 0, but I still need to see it in your distribution. And then we have a 6 out of 10 chance of getting a $1 bill, which means our value is -4. We paid $5, but we're getting $1 back. Okay. First of all, do our probabilities add up to be 1?
Yes.
Good. Our mathematical expectation then would be positive 15 times 1/10, positive 5 times 1/10, plus 0 times 2/10, plus -4 times 6/10. We might not even need a calculator for this. How many tenths do we end up with? We would have 15 plus 5 plus 0 minus 24. -4 tenths. Every time you play the game, you can expect to lose 40 cents. Now, if you play it only one time, you cannot lose 40 cents. That's not possible. But the more times you play, the more it's going to even out to be that 40 cents each game. Okay? Which means if you play 100 times, the expected value is what? Ugh. You are going to lose $40 if you play 100 times. You would lose $80 if you played 200 times. Okay? If you played 1,000 times, you would lose $400. Okay? Okay, now, we personally probably wouldn't play 1,000. Okay? Or I would hope not. Okay? Mathematical expectation, the more times the game is played, the closer this value will be to the actual money you're taking in or losing. Okay? So if this game is at a carnival and 1,000 people come to play it, then that dealer should walk away with darn near close to $400. Okay? That is what is expected if everything is random in the game. Okay? What questions do you have? Okay.
What was the question?
I said, what questions do you have?
Oh.
It's not a complicated one.
That's the question because you're like.
Okay. There's something else I wanted to point out. Sometimes your sample spaces will be easy to just list out. Sometimes you're going to have to make a tree diagram. What I want everybody to do is turn it over to your homework side, and we are going to get through number 1 together. Okay. So first of all, do you see how I have 5 games listed? And for each of the 5 games, I want you to answer 1 through 6. And it's the exact same 6 questions that we just went through in our notes. Okay? After you've done this for the 5 games, then you can go down here to 7 through 10, and it asks you to compare the 5 games. So let's look through low, lower, lowest. The house will roll a die. The player must roll a number that is lower than the number that appears on the die of the house. If the same number is rolled by both the house and the player, then it is a tie and neither wins. the payoff is equal to the amount wagered. Okay? Just go ahead and use $1 as your amount wagered. When we go to make our games on Monday, we won't be using dollars, we're going to be using Tootsie Rolls.
Oh, I thought we were gonna use Monopoly money.
That would be fun, but I don't have enough Monopoly. But I have a ton of Tootsie Rolls that we're going to bet with Tootsie Rolls. Okay? So what I want you to do, because for low, lower, lowest, number 1 is create your sample space. The house is rolling a die. How many different ways can they do that? Write it out. 1, 2, 3, 4, 5, 6. Probably on another sheet of paper. I'll be checking it, but it can be like with your daily work. Okay. Now, after the house rolls a die, what do you do? Okay. So you could roll a 1, 2, 3, 4, 5, or 6.
Do we have to write like all of them? Like do you want us to actually?
This is Greg.
Do you want me to help you, or do you want me to just throw you to the fishes?
I'm saying it's Greg for the person rolling the second person rolling the die.
You don't know. Let's figure out the mathematical expectation, and then we'll see if it's rigged. How many different possibilities do we have? We have 36. 6 times 6 is 36. Okay, so at your pod, I want you to work on probability of winning, probability of losing, and creating your probability distribution.
Okay, so we do that with probability.
Yeah, that's fine.
Well, shouldn't it be close to the same thing?
Pick a pass. I lost.
Oh, you don't have a bathroom pass.